Population genetics is a science that deals with genetic variation within populations and with the forces that change this variation. In this course, we're just going to barely scratch the surface of population genetics, but we will go into some aspects of it, since it is a way of thinking about stringent ways of describing the processes that are involved in evolution, in natural selection and in evolutionary processes more generally. We will, however, only look at some very simple examples just to give you an idea about the types of things that one can look at. We will also use it as a way of starting to think about how to model biological systems, how to set up a simple model of some biological system, how to fit such a model to data, and how to maybe think about consequences of aspects of your model, what different parameter values in your model will mean. So, to keep things simple, we'll be focusing on a system where we have, imagine we have a set of asexually reproducing organisms that breed every generation and then die. So this makes things a lot simpler. So imagine, for instance, that we're looking at an organism that every generation produces, an organism that every generation produces 200 offspring and then dies. So 200 is a number that we refer to as the fecundity of this organism. Imagine that for various reasons, only about 2% of the organism's offspring survive. This is called the survival rate. Oh, if I can get this to work. Survival rate. You can see that this means that for this particular organism, only a total of 200 times 2%, corresponding to 4 individuals, 4 offspring, will survive long enough to get offspring of their own. R is what we call the per capita reproductive rate of this population. So how would a population with these characteristics behave? Well, you can see that every individual leaves a total of 4 offspring. Every individual that was present at some time will leave 4 offspring that will breed and go into the next generation. So this means the population will increase. But let's start to think more stringently about how exactly the population will increase. First of all, if we call the initial number of organisms that's present at the start of the experiment N0, then you can see that the number of organisms present after 1 generation, N1, must be equal to N0 times R. For every individual that was present in time 0, there will be R individuals present after 1 generation. So there will be R times N0 individuals at time point 1. This is also true of time point 2. The number of individuals present at time point 2 is equal to the number of individuals present 1 generation previously, time point 1, times R. However, we know, of course, that N1 was the same as N0 times R. So the number of individuals at time point 2 is N0 times R, or said more succinctly, N0 times R squared. More generally, you can probably see that if we continue this line of thought, then after t generations, the general expression will be that there will be N0 times R to the t individuals present at that time point. This sort of relationship is called exponential growth, and you all know how this looks. It's a steeply increasing curve, a bit like this. If we have generations on the x-axis, and population size on the y-axis there. Obviously, exponential growth is a very simple model of population growth. You can see that the way it keeps rising and rising and rising is not realistic in an actual biological system. In an actual biological system, growth will be limited by finite resources such as space and food, etc. It is a good model of initial growth under some circumstances, like for instance bacteria growing in a test tube, or maybe larger animals that have arrived in a fairly unoccupied ecological niche. In this context, it's mostly a way for us to think about growth and other aspects that are important to understanding the processes of evolution. So for now, we'll just keep things simple and assume that when populations grow, they grow according to this exponential model. Okay, so this is how a population will grow if it does live under these conditions. So let's imagine now what happens if we have a population that consists of two different alleles, which we will call uppercase A and lowercase a. The two different alleles could be different in having maybe just a single nucleotide differ between their genes, or it could be more extensive differences. We are going to assume that they are present at different frequencies, f uppercase A and f lowercase a. For the starting case, we're going to assume that their per capita growth rates, Ra and R small a, are the same, and that they are therefore the same as the per capita growth rate of the entire population. Incidentally, the per capita growth rate of a genotype is known as that genotype's absolute fitness. Okay, so let's now explore what happens when a population containing two such alleles grow. First of all, we can see that the initial number of uppercase A present must be equal to the total number present at time 0 times the frequency of uppercase A. Similar expression can be written for lowercase a, of course. After one generation, we know from previously that the number of organisms present after one time point is the same as the number of individuals present initially times the growth rate. Same is true for lowercase a, which we can write over here. This means that the total population size after one generation can be found as the sum of uppercase and lowercase a individuals, and we can insert the expressions we have for those here. So let's just rearrange them slightly to make it a bit simpler. Plus 0 times R f lowercase a. You can see that there are some terms that are occurring in both of these. We can put these outside a parenthesis, and then we have an expression like this. Now, we know that since this population consists only of uppercase and lowercase a individuals, that the two frequencies must by definition sum to 1. So in this expression, they go out, and all we have left is in 0 times R. Now this means that we can now actually compute the frequency of A after one generation, because this is the number of uppercase A after one generation. This is the total number of individuals present after one generation. So going into the corner here, the frequency of uppercase A after one generation is the number of uppercase A after one generation divided by the total number of individuals present after one generation. You can see that these terms cancel out, and the not so rocket sciencey conclusion in this case is that the frequency of uppercase A after one generation is the same as the frequency of uppercase A when we started the population growth. So despite the fact that both uppercase A and lowercase a allele populations are growing exponentially, like this over time, if we look at the frequencies of the two genotypes in this case, where they have the same absolute fitness, then those frequencies will be constant. That's supposed to be a flat line. It's hardly rocket science, but still it tells you something fundamental. Different alleles having the same fitness will not change their frequencies. Okay, so let's now have a look at the more interesting situation where the two genotypes have different fitnesses. So we again have these two genotypes. They again have distinct frequencies, but now they also have distinct fitnesses. Remember that the absolute fitness of a population, and therefore also the absolute fitness here of a genotype, is based on fecundity and survival rate. So imagine, for instance, in this case, that uppercase A has an absolute fitness of 4 and that lowercase a has an absolute fitness of 2. These differences might be caused by, for instance, uppercase A having a fecundity of 200 and a survival rate of 2%. Lowercase a might have a larger survival rate, a larger fecundity. It might make 400 offspring per generation, but it might have a much lower survival rate, say 0.05%, ending up with an all-in-all lower absolute fitness. So fitnesses are the sum of many distinct terms. In the simple world that we're looking at here, we're just looking at overall fecundity and overall survival rate. And these are the things that natural selection will work on. Let's now think what happens when we have a population with these two genotypes growing. So again, we can write expressions for how many uppercase A and lowercase a we have at the initial time points. And these are the same as before, of course. It's the total population size times the frequency of that allele. After t generations, we know from before that the number of individuals will be after t generations is the same as the number of individuals at time point 0, that's this, times the per capita growth rate to the t. In this case, that's specific for each individual allele. They have different, absolute fitnesses. So we can write the same expression here, the corresponding expression for lowercase a. So now these r's, these absolute fitnesses, are different. This means that the total population size at time point t is the same as the sum of the uppercase A and lowercase a populations can now be written by inserting all of these in the expression. I to the t. Okay, we can now compute the frequency of uppercase A after t generations. This is the number of uppercase A after t generations. This is the total number of individuals after t generations. This means that the frequency of uppercase A after t generations can be found by dividing the number of uppercase A by the total number of individuals at that time point. I'm just going to write this out. Oops. I to the t. Okay, so we can simplify this expression a bit by removing the n0, which is on all of these terms. We can further simplify it a bit by dividing both the numerator and the numerator and the denominator by r uppercase A to the t. So we divide by r uppercase A to the t. Divide by r uppercase A to the t. Now, what will this give us? In the numerator, the r uppercase A to the t's will cancel out, leaving us with just f uppercase A. In the denominator, again, on the left-hand side here, the r uppercase A to the t's will cancel out, and we'll get just fa. On the right-hand side here, we'll have a slightly more complicated term, f lowercase a times r lowercase a to the t divided by r uppercase a to the t. Now, r lowercase a to the r lowercase a divided by r uppercase a is referred to as the relative fitness. Okay, usually refer to that by a W. So the relative fitness of an allele is the absolute fitness of that allele divided by the absolute fitness of some reference genotype. Typically, the reference genotype is the one with the highest fitness. Okay, so we take lowercase a divided by uppercase A in this case. This we can now insert into the expression, giving us finally a formula for how the frequency of uppercase A changes over time when two alleles have different fitnesses, meaning when there's natural selection. And it will look like this. So what is this expression telling us? This expression is telling us that after t generations, the frequency of uppercase A can be found from the initial frequencies of uppercase A and lowercase a, and from the relative fitness of lowercase a relative to uppercase A. This is an important result. I mean, this is a fairly simple model, but nevertheless, it shows us something interesting. It shows us that the absolute fitnesses don't actually matter for how these frequencies change. All that matters is their relative value. So it doesn't matter if uppercase A has 4 and lowercase a has 2, or if uppercase A has 10 and lowercase a has 5, or even if uppercase A has 0.5 and lowercase a has 0.25, meaning that the populations are declining in size. In all of these cases, because the relative fitness is the same, the frequencies will change in the same manner. You will explore this in the exercise, but I'll just maybe show sort of how it looks. If we have one allele with a higher fitness and one allele with a lower fitness, these frequencies will change something along these lines. After a number of generations, the most fit allele will essentially reach fixation. As we say, it will be the only allele that's present in the population. So these are obviously extremely simple models of growth and selection that we've been looking at, but they nevertheless capture some essential aspects of the biological systems we're thinking about. We have different genotypes, they have different fitnesses. These different fitnesses are the product of various terms, like in this case we looked at fecundity and survival rate. The genotype having the highest fitness, the genotype that leaves the most offspring, that itself begets more offspring, is the allele that will increase in size. And we can even come up with equations telling us what to expect in terms of how these frequencies will change. If the two, and importantly, all that matters for how these frequencies change is the relative fitness, not the absolute fitnesses. If the two alleles have the same fitness, meaning that there's no fitness difference, it's what we call a neutral difference, then frequencies will, in principle, remain the same over all the subsequent generations.